I find it very frustrating that our education system very often demanded that we had to make a choice. Was it Shakespeare or the second law of thermodynamics? Was it Debussy or DNA? Was it Rubens or relativity? Were you going to be an artist or were you going to be a scientist? I grew up here in Oxfordshire, and when I went up to a comprehensive school not so far away from here, I was very excited by the opportunity to start doing scientific experiments, learning about the science of where we'd come from, what was going to happen next. I fell in love with the power of science to understand our place in the universe. But I also had the opportunity to do theatre at my school. I remember my music teacher asking us, anyone want to learn a musical instrument? And three of us put up our hands. We were led into the storeroom cupboard where it was very bare except for 3 trumpets, which is why I ended up learning the trumpet with 2 of my friends. So I found this very frustrating, that I seemed to have to make some choice in which direction I was going to go in. I sort of wanted to go in both. And then something very lucky happened to me. I had a wonderful maths teacher at my comprehensive school who, in the middle of class, said to Sautoy, "I want to see you after the class." I thought, oh, I'm in trouble now. So he took me round to the back of the maths block, and I thought, I'm really in trouble now. What's going to happen? And he then recommended some books that he thought would open up the world of mathematics to me. And those books, I actually came with my dad up to Oxford that weekend. We went to Blackwell's to get these books. I was amazed by this shop, little shop front, and then you go in, it's like the TARDIS, suddenly there's huge inside. And we got these books and I took them home and I started to read about what mathematics was really about. Because as my teacher said, it's not what we're doing in the classroom. That's all just the boring kind of grammar of the subject. There's so much beautiful stuff hiding that we don't tell you about. And there was one book in particular that resonated with me very significantly, and it was A Mathematician's Apology by G.H. Hardy. This, I can see some nodding. I've talked about this book before because it has been so instrumental in making me who I am. This book is written by a Cambridge mathematician, a number theorist. I think he wrote it in the 40s, 1940s, and he describes what it's like to be a mathematician. It's not about mathematics, but about being a mathematician. And he describes it as being like an artist. He wrote, "A mathematician, like a painter or a poet, is a maker of patterns. I'm only interested in mathematics as a creative art." And as I began to explore more and more about the mathematical world, I realized here was the place that I could actually fulfill that creative desire to tell stories or to do something creative, yet still here was the language of science which told me how the universe worked. It was a perfect bridge between those two worlds that I seemed to be being asked to choose between. So I decided to become a mathematician, and I realized my dream. Here I am as a professor in the department in Oxford. But through the years that I've been a mathematician, I've always still kept a big connection to the arts. I used to go down to the Pegasus Theatre and do theatre there. I played trumpet in the orchestras here. It's still been a very important part of my life. But one of the interesting things as I've made my journey as a mathematician, being invited into the rehearsal space by people like Complicité or the concert hall or the artist studio, it wasn't just a matter of the fact that I was kind of vicariously enjoying being part of that artistic world. As I started to work with these artists, I began to realize that there was way more connection between the mathematics that I was doing and what they were doing. Because the things that they were interested in, the structures that they enjoyed composing within, painting within, writing inside of, time and again, those structures I recognized as things that were mathematical. And I would say, well, but that's a piece of mathematics. And they go, I don't think it is. And as I explained, no, that's something I'm interested in from a mathematical perspective. I realized that it was so much more connection. And in this book, new book that I've written, which is kind of, is in some sense, the stories of the time that I've spent with many of these artists. One of the things I do is to define mathematics. I mean, how do you define mathematics? Often when I go into a school, I ask kids to define it, and it tends to be, about calculation or solving problems. But for me, mathematics is the study of structure. That is what we do. I see you're not quite sure about that, but I think structure is actually, very much, that's the thing we're often interested in. And of course, for an artist as well, you see, I think structure is hugely important. I think that a lot of people think surely mathematics and the arts are polar opposites, chalk and cheese. Maths is a cold, logical subject about truth. The arts is about expressing your emotions and ambiguity and something, maths is cold, art is hot. But actually, as I studied with a lot of these artists, I realized that's not true at all. For many artists, structure is hugely important to their discipline. And I like this quote by Stravinsky, who said, well, I can only be creative under huge constraints. And oftentimes an artist enjoys the structure in order to push them in interesting new directions. Stravinsky went on to write, the musician should find in mathematics a study as useful to him as the learning of another language is to a poet. Mathematics swims seductively just below the surface. So I think this is I tell some of the stories about Philip Glass, who I've done some work with in America, and he told me, look, emotion is about the last thing which comes out of artistic practice. The emotion emerges out of the structure. And so structure is an incredibly important part of doing art. And somehow it's not about the emotion first, structure first, and then often the emotion emerges out of that. So this has led me to write this new book, which will be available afterwards, and I'm happy to sign copies for you, which is a story of how many times artists often use mathematical structures in their own work. One of the interesting things is sometimes they do it consciously and they learn about the mathematics, and I'll tell you some of those examples. But quite often they're drawn to these structures quite intuitively because of their aesthetic value. There's something beautiful about them, and it's only later that we discover that is a piece of mathematics. So I suppose if I was going to, I've called the book Blueprints because these mathematical structures, I think, are like blueprints which different artists then use in different ways. And I've broken the book up into 9 different mathematical blueprints, which are then a kind of launching pad to see how different disciplines use those blueprints in different ways. How does a writer use a structure in comparison to an architect or a visual artist? If I was going to do a blueprint for the book, I think it would be the simple triangle with at 2 corners I've already mentioned. One is the corner of mathematics. The other corner is the corner of the arts. But I think what unites both of these is something to put at the top of this triangle, which is the natural world. Because oftentimes the structures that I'm interested in mathematically, and the structures that artists are using often are already there in nature. And if you think about it, mathematics was created as a subject to try and understand our place in the physical world. We're trying to understand the structures of the universe. And artists in their turn, I think, are responding quite often to structures that we see in nature. So I will show you that structures that I'm interested in mathematically, that artists might also be interested in, quite often we'll find them already being used creatively by nature. As I've said, I've broken the book into 9 different blueprints. Some of them will be quite expected, I suppose, if you know about mathematics in the creative arts. For example, the Fibonacci numbers and the golden ratio in there. But what I thought I would do in this talk is to take you to some of the more unusual blueprints that have been used by artists. So I'll do a little tour of a few of the blueprints in the book and show you in particular this kind of interesting way that different artists from different disciplines have been inspired by the same structure. So the first blueprint in the book is actually somehow the blueprint for the whole of mathematics, because it's the prime numbers. This is part of my area of research of prime numbers. Primes are the indivisible numbers, 2, 3, 5, 7, 11. Out of the prime numbers, of course, you get all other numbers by multiplying primes together. From numbers, you get mathematics. From mathematics, you get science. So in a way, these primes are right there at the beginning, the blueprint of everything. It's the first chapter in the book, and I start with a story of a musician who used these prime numbers very intriguingly in a piece that he wrote in the 20th century. This is the composer Olivier Messiaen. Actually, I fell in love with Olivier Messiaen as a trumpeter. I used to come up every Saturday to the Oxford Youth Orchestra here, and one weekend the conductor from the London Sinfonietta brought the Tarangolila Symphony parts, and we spent the whole weekend playing this piece of music, which is the most incredible piece of music. I think my trumpet playing was at its best that weekend. I think it's gone down ever since, and Messiaen writes great trumpet parts. But the piece I want to talk about is actually a rather small scale piece, actually one of the most famous pieces of the 20th century. It's a piece called The Quartet for the End of Time. This is a piece that he wrote while he was a prisoner of war during the Second World War, when he was in Stalag 8A. And he had, there was a rickety upright piano in the camp, and he found 3 other musicians who were also in the camp, a clarinetist, a violinist and a cellist. And he decided to write a piece for the 4 of them, which was eventually performed on the 15th of January 1941 for all the other people in the prison camp. It was so cold that it was described, that concert, that the clarinetist's fingers froze to the metal of the clarinet. But the piece was so magical that many of the people in the camp had never been to a concert before, but what they experienced was one of the most extraordinary pieces of music that's been composed in the 20th century. It starts, the first movement is called the Liturgie de Cristal. And it starts with the violin and clarinet exchanging bird themes, one of Messiaen's obsessions. But it's in the piano part where there's an extraordinary bit of mathematics going on. The piano part is very repetitive in some ways. And here's the score for the piano part. There's a 17-note rhythm sequence, which starts crotchet, 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 and then goes off in a lovely syncopated rhythm, then ends crotchet, minim, and then starts again. So all he does is just repeat this rhythm sequence over and over again throughout the whole piece. Completely patterned, but the harmonic sequence is 29 chords, which get played repetitively over and over again. So the 29 chords go up to this point here. But the clever thing that Messiaen has done is to choose 2 numbers, 17 and 29, which are prime numbers. This has the effect that although there's a huge amount of repetition in rhythm and harmony, when you put the 2 together, there's no repetition that happens at all during the piece. You have to hear 17 times 29 chords for the thing to come back into sync and be repeating, by which time the piece is actually finished. So if you think about it, the rhythm starts off, but when rhythm starts again, the harmony is still about 2/3 of the way through its chords. The harmony starts playing again, and the rhythm is somewhere in the middle of its kind of second repetition. So you have these 2 things which are just completely out of sync. And the piece is called the Quartet for the End of Time. Time requires us to keep track of things which repeat. So I'm not sure whether he intended this, but by using these primes, nothing quite repeats. And so you don't have a sense of time in a way. I'll just play you a little bit of the opening so you can hear the piano part and and how these chords and syncopation work. Now the rhythm starts again, but the chords are still working their way through the 29 chords. And then as the 29 chords play out, they start again, but the rhythm is somewhere completely different. Now I actually was intrigued to know whether Messiaen knew his mathematics, and that's what he programmed in there. Because he's actually a character who comes up quite a lot in the book, because a lot of his music uses ideas of symmetry to make new scales. He understands, in one piano piece, he creates a completely new symmetry that's in a very high dimensional space. But I asked George Benjamin, who's a composer who worked with Messiaen, how much mathematics did Messiaen know? And he said, no, he wasn't formally trained at all. And here's a very good example of a musician that was drawn to structures that worked musically for him, which in retrospect had some mathematical significance. So it was the music that was helping him to find these structures, not that he learned about mathematics and then programmed it in. There's a very contemporary musical example of the way primes can keep things out of sync, which is Radiohead. Radiohead, most pop music is incredibly boring because it just comes in 4/4 and it repeats itself way too quickly. But why Radiohead is one of the best bands ever is that they love disrupting rhythms, and when you listen to a piece of Radiohead, you're never quite sure where the beginning is, what's repeating. Here's one famous example where somehow you just can't work out how many beats there are in this bar. This piece is made out of 5, 6, 4, 7s, and it's shifting all the time. You never quite get any sort of feeling of stability in the piece at all. And it didn't surprise me to find out that Johnny Greenwood, who writes a lot of their music, also in his youth orchestra played some Messiaen and fell in love with Messiaen too. So I think he probably saw some inspiration from the mathematics that Messiaen was using. Now, as I said, quite often structures, clearly the primes are important to me as a mathematician. They're our greatest unsolved problem, understanding any pattern in these numbers. A lot of us are working here in the department trying to understand primes. They're used musically, but they also have their origins in nature. Fibonacci numbers are things which are all over the natural world, but primes are actually quite hard to find in nature. But there is an example of primes in nature which is doing exactly the same trick as the way Messiaen is using them. This is my favorite insect, which I've talked about a lot. If anyone's come to my talks, I seem to bring these cicadas into every talk because they're my favorite insect. I mean, if I was cast out on a desert island and I had to take one insect with me, it would be this cicada. It has an amazing life cycle. It hides underground for 17 years doing absolutely nothing. And then after 17 years, these cicadas emerge into the forest. They sing away, or at least half of them do. The males sing away to the females. The sound of the forest, there's several million of these, is so loud that many residents move out of the area when they appear. There's even, I went to, did some filming for the BBC, and we went to Nashville, where a 13-year life cycle cicada was emerging. And we were having breakfast, and the waitress said, "Yeah, I remember when I was at school when the last time these cicadas emerged, and and we've had quiet up till now." And she said, "We even have a website here that if you're planning your wedding, you can go online to check that you won't be having your wedding at the same time as the cicadas because they're so loud you can't actually hear the marriage vows." So, but they party away and they lay eggs, and then the forest. They all die. That's actually really dangerous because there's so many cicadas all over the place. You get cars planing across all of these cicadas. And then the forest goes quiet again for another 17 or 13 years. But there's no cicadas with a 12, 14, 15, 16 or 18-year life cycle. So what is it about the primes that seems to be helping these cicadas? Well, we're not sure, but we think it's the same kind of trick that Messiaen was using. We think there was a predator that also used to appear periodically in the forest and used to try and time its arrival to coincide with the cicada. So let's do a little example. Let's suppose the predator appears every 6 years. Now, a cicada that appears every 9 years is going to get in sync quite quickly with the predator. Every second time it appears, there are predators there which will wipe it out. It's the same with Messiaen. If he'd chosen, say, 18 and 30, the thing would get into sync too quickly. It's the primeness of 17 and 29 which is keeping things apart. So if we change the cicada to 7 years, it's appearing more often in the forest, but because 7 is prime, it keeps the cicada out of sync of the predator, and it can survive until year 42 before it meets the predator. So here we see the same kind of dynamic that Messiaen is using. Instead of the cicada and the predator, we have the rhythm and the harmony, and it's the primeness which is keeping those things out of sync. So a nice example of it already being used in nature for the evolutionary survival of this cicada. Well, how are primes used across different disciplines? Architecture is one of the things I talk about a lot in the book. And architecture, in some ways, you would expect there to have to be a connection between the arts and the sciences, because you want your building to stand up. So architects often are very good mathematicians. The primes are used in architecture quite often for concert halls in order to create great acoustics. If you have a flat wall, that's hopeless, because you'll get bouncing echoes, dead spots, places where you'll just hear the cellos or the brass. In order to create a really good concert hall, we now understand that having kind of things sticking out of the wall connected with the prime numbers ensures that wherever you sit in the audience, you will get a full experience of the orchestra and all of the waves from the orchestra. So primes are very important in acoustics. Now, one of the places I think people, okay, so yeah, sure, maths is going to be in architecture. There's a lot of connection between music and mathematics. Visual art, as I'll show you, there's a lot of mathematics there. But I think often people think, well, surely the written word, where's the mathematics in novels or poetry? Yes, because poetry, of course, has some structure and rhythm and rhyming structure. But I think it's more of a challenge to find, for example, prime numbers in literature. Well, it turns out there's a very beautiful example of an author that uses prime numbers to an amazing effect. And this is William Shakespeare. William Shakespeare, of course, we celebrate as a great wordsmith, but I was quite surprised to discover he was actually very interested in number as well. And he uses numbers almost as a code in his writing. So we're all familiar with the fact that Shakespeare writes things in iambic pentameter. 10 syllables, 5 groups of 2, short, long, short, long, short, long, short, long, short, long. But when Shakespeare wants you to take notice and to wake you up, in case you've been lulled into a sense of sleeping to the iambic pentameter, he changes it to a prime number. So what is the most famous line in Shakespeare? To be or not to be, that is the question. It's 11 syllables. So in Hamlet, you know, you're sort of slightly dozing off with this iambic pentameter, but Shakespeare wants to wake you up. And so he chooses a rhythm which is quite disruptive. It doesn't fit into a pattern. And suddenly you are woken up by this odd beat at the end of this. Macbeth as well. Is this a dagger which I see before me? Is also 11 beats. He's doing this very consciously because the whole thing is then 11 beats. In contrast, if he's writing about magic, the number of syllables goes down to 7. So Midsummer Night's Dream, one of the plays I did here as a student in Magdalen Deer Park, I was Flute the Bellows Mender. Where, of course, Puck administers the love potion to change who the lovers are falling in love with. And as he pushes this into the eyes of the lovers, here we hear 7 syllables. Churl, upon thine eyes I throw, all the power this charm doth owe. Beginning of Macbeth again, the witches, when shall we three meet again? It's 7. 7 is being used by Shakespeare to tell you that magic is afoot. And actually, people didn't like these odd numbers. James I tried to ban the use of any odd number syllables in poetry. He wanted things in 2s, 4s, 8s, and 16s. But Shakespeare enjoyed kind of disrupting this. And I think, you know, if you look at the science at the time, Shakespeare was around when John Dee was producing the first editions of Euclid published. Galileo comes up with the idea of the sun-centered solar system. And in fact, Cymbeline, you can see, is a whole discussion of the change in the way we look at the solar system. So Shakespeare was very sensitive to a lot of mathematics. There's one poem in particular which is dripping with primes. It's called The Phoenix and the Turtle. It's an allegorical poem. And again, it's in 7 syllables. The number of stanzas is prime. The number of total lines is prime. I discovered this actually. I play for the England Writers football team, and we were playing the Swedish Writers football team, and I'm playing defence, and one of my fellow defenders, he's a Shakespeare scholar, and he turned to me and said, "Oh, I've got to tell you about this poem," and he started telling me about this allegorical poem with all of these primes, and I was like, "Wow, that must have been doing that deliberately." So we got very excited until we'd seen that Sweden had scored several goals whilst and our strikers were going, "Well, what are you doing back there?" And then we're talking Shakespeare, and oh, that's all right then, because we're all a bunch of writers. So I think primes are quite interesting in the way that they're used across different disciplines. So now let me take you to a more visual blueprint. There's some numerical ones like the Fibonacci, but we'll have a look at the fractal one, because obviously fractals are kind of interesting geometric shapes. A fractal is a shape which is kind of very complex shape. When you zoom in on it, it never seems to simplify. This is the property of a fractal. It's somehow scaleless. And a rather beautiful example of a fractal, if you're like, I'm not quite sure what you're talking about, is actually the work of Jackson Pollock. Because Jackson Pollock's paintings are so special because what he is doing is to paint a geometric shape which actually is something we recognize mathematically as something called a fractal. So a lot of people say, "Oh, come on, why is this so sell for so much money?" I think it broke some of the records, some of these Pollock's, for the highest amount of money spent on a piece of art. Surely anyone could do this. You just flick a bit of paint around and you've got a Pollock. But actually, Pollock was doing something rather special. And I tell a story about 20 canvases which were revealed in somebody's attic, that they said, these seem to be some unknown Pollocks. And they were eventually revealed to be fakes, not by artists or art historians, but by a mathematician who analyzed them and showed they didn't have this fractal quality. So let me show you an example. So here's a painting, and I've taken the painting, and then I zoomed in on a section, and then I zoomed in even further, and then a fourth zooming in. And the idea of a fractal is you can't really tell at what scale you are. And I think you probably tell which is the most zoomed in, because eventually you have to see the paint somehow. The most zoomed in is the top right-hand corner. But which of the other 3 is the original painting, which one the next zoom in? It's actually quite hard to tell. I mean, the original is the top right, top left. And I think this is what's so lovely about being in front of a Jackson Pollock, is that you lose yourself. You lose a sense of scale and you almost fall into the painting. You don't quite know, am I near or am I far away from this? And the reason that he was able to create this kind of unique geometry is his style of painting. If you've seen any videos of the way that Jackson Pollock paints, it looks like he's quite drunk when he's painting. In fact, he was quite a drinker, so perhaps he was drunk when he was painting. Actually, often it's said that he was drunk, but his best paintings were done during a period when he wasn't drinking so much. He did actually drink too much, so he died in a car accident from drink driving. But you see, if I was going to make a Pollock, I would dip my paintbrush in the paint pot and I would start flicking like this. And everything would be from the elbow. It would be, and I've just been using a sort of regular pendulum is the way that I would be flicking my paint. But Pollock was doing something else. He actually was making what's called a double pendulum. So he was moving his shoulder at the same time as his elbow. And so what he was creating was, I mean, a simple pendulum like this is very regular. But if you have a double pendulum, you get something called chaos starting to happen, which is very unpredictable. And the geometry of chaos, when you then put a paint pot on at the end of this, is to produce these fractal geometries. So there is a way to fake a Pollock. which is you take a chaotic pendulum, which somehow the top is moving as well as the axis in the middle. And I actually tried to do this. We went to Jackson Pollock's studio and we set up a kind of chaotic pendulum with a paint pot. So here's my attempt at a Pollock using this chaotic pendulum. I put this on eBay, but it didn't sell for very much, unfortunately. But now Pollock, I think again, here's an example. He didn't know what he was doing. He didn't know about fractals. In fact, it was very late, this discovery by a mathematician of the fractal quality of his paintings. But fractals are essentially the shapes of nature. Nature grows things in a very fractal way. And when we went to Pollock's studio, it's surrounded by forest. And a tree is a very good example of a fractal. It's got a huge, great big trunk, and then branches, and then smaller branches, and then twigs on those, and smaller twigs. And each bit is sort of like a copy of the larger shape. And if you're an animator and you want to create kind of shapes which have a kind of natural feel to them, often you'll use these kind of fractal ideas to generate a fern or a tree. And so Pollock was arriving in his studio, seeing all of these fractals around him in the nature, and he was using his technique to somehow abstractly capture the fractals that he was seeing in the natural world in this abstract expressionism. So it's again, here's the artist responding to the natural world, and now we understand the mathematics of the natural world is very often these fractals. So here's an artist who was using it quite intuitively, but there are other artists who understood the mathematics and then would apply it in their actual painting. So Salvador Dali is somebody who loved spending time with scientists. He used to say that I like to swim in the hot waters of science rather than the cold waters of art. And he's somebody who spent a lot of time informing himself about ideas of mathematics and physics. You remember, of course, those very famous things inspired by relativity, the kind of watches melting. But here's an interesting example called the Visage of War, where he's taken a skull with 3 holes, and in those holes he's put another skull who have 3 holes, which he's put another skull inside. And so the effect is to create this kind of fractal geometry, something we call a Sierpinski gasket, which is this kind of mathematical object on the other side. One of the most famous fractals, of course, of all time is the Mandelbrot set. This inspired a lot of graphics during the 90s. When I was clubbing, you would go to clubs and this would be projected onto the walls, and you spatially feel that you were dropping into this shape. And one of the exciting things is that the mathematics allows it to go on to infinity. There's a tension which comes up in this book, actually, which is that mathematics can often allow things to be infinitely explored like this fractal, but actually in nature we have limits. A quantum limit will emerge where I will not be able to go any further and zoom in on this. Even in Pollock's case, at some point we saw the pixels of paint. So mathematics can often do things kind of in this infinite way, which can't actually be replicated in nature. But these have been the inspiration actually for some interesting things in the film industry. So I went to pixel animation on one project I did, and there they were using fractals to actually create a lot of the kind of backgrounds for their animations. One we looked at in particular was the film Up. Beautiful film with the grandpa and the balloons and things like that. But they end up in the jungle, if you remember. And in the jungle, all the scenes there were created not by artists, but by mathematicians who were using fractals to create these environments. But then the more recent example has been the Marvel Universe has wanted to actually create kind of 3-dimensional fractals, 3-dimensional versions of the Mandelbrot set. And for some time they saw these 2-dimensional pictures, were quite excited by it, but there didn't seem to be any 3-dimensional versions of the Mandelbrot set. And it took some time for mathematicians actually to tease out how to make an interesting 3-dimensional shape with a particular equation. And eventually this thing called the Mandel bulb was discovered, and this has been used by the Marvel Universe. For example, the Guardians of the Galaxy, they make the planet Ego, and it's made purely with these mathematical shapes in order to create these kind of strange new worlds. What about the written word? Again, that seems like, well, how on earth do you have a fractal in writing? There is a beautiful example of a play that talks about fractals. Many of you probably have seen Arcadia, Tom Stoppard's maths play. It's a wonderful play, and it talks about the ideas of fractals actually in the text. But the beautiful thing is that not only are fractals talked about in the text and chaos theory, but the way Tom Stoppard structures this play is actually a fractal. Because it's a play in two time zones. There's a contemporary story and a story 17th, 18th century. The historical story is over a 3-year period. The modern story is over a 3-day period. And what you see is complete copies scaled out in the historical story and the modern story. I mean, I've talked to Tom Stoppard, and he very deliberately did this. And he wanted this kind of idea of the fractal structure of the modern story to be reflected in the historical story as well. So a beautiful example of talking about fractals, but actually making the play a fractal itself. Right, I'm going to take you to another geometric blueprints. One actually that when you came in you will have seen a lot of examples. These are the Platonic solids. I did an event a couple of weeks ago with Conrad Shawcross in London, and he's somebody who's been obsessed with mathematical ideas. As you can see, his sculptures all around our department. And in particular, he's been very fascinated by the power of the Platonic solids, which are the shapes that, if you're a Dungeons and Dragons fan, you'll know that dice can be 5 different shapes, including the cube, but here, for example, the dodecahedron. So these are very physical objects, and I'll show you how they're used in the visual arts. But one of the most interesting examples where Platonic solids have been useful as a blueprint for artists is in choreography. So the story about the chapter dedicated to Platonic solids, I actually talk about the way that Rudolf Laban, who's one of the great choreographers, innovators of the 20th century, used Platonic solids in a very fundamental way to create his kind of dance style. So he also created an incredible sort of notation system to be able to record how do you actually record what a dancer does? If you think about music, we have a notation for recording music, but choreography doesn't have a universal notation to say what it is the body is doing. But what Rudolf Laban wanted his dancers to imagine is that they had a Platonic solid which was sort of inside which they were encased, and their limbs needed to move along the edges of these Platonic solids. And so you would have this kind of independence of movement as the legs and arms and head and torso would move along the lines of the shapes. And he found that some shapes were much more close to the way the human body likes to move. So, for example, the cube didn't work at all. It did not fit the way that a body wants to move. He found that the icosahedron, this shape with which is made out of 20 equilateral triangles, was the shape that somehow the human body likes to move inside. And he wrote, man is inclined to follow the connecting lines of the 12 points of an icosahedron, with his movements traveling, as it were, along an invisible network of paths. And the notation that he used would therefore be which limbs, how long you would spend on them, and where they would be on the icosahedron. He was quite keen to create choreography that could be replicated across a country, for example. He was asked to produce a choreography for the Munich Olympics in the 1930s, Berlin Olympics, was it Munich or Berlin? And he decided that it was going to be something that dancers across Germany would learn, and his notation meant that he could actually communicate what they did. He also created like scales, so you can, if the 12 points of an icosahedron, it's actually quite an interesting puzzle. Can you go between all 12 points once and once only around the shape? And you can do that, and there are many different ways to do this. And he created kind of movement scales, which were a Laban dancer learns in order to map out the 12 different points on the scale. Platonic solids have been an inspiration for artists right back to when we first started making anything of an artistic kind of quality. In Oxford, we have in the Ashmolean these amazing Platonic solid stone balls, which if you haven't seen them, go and have a look in the Ashmolean. They're about a fist size, but they're very curious because we're not quite sure what they're for, but the artist who's been making these has been carving out kind of patches on these stone balls and is exploring how to symmetrically arrange them. And way before Euclid and mathematicians discovered these shapes, you already see the artists are teasing out what might be possible. And there are quite a lot of stories in the book about how artists are actually the first to discover things through playing, and then the mathematicians, we've understood how to classify them. So it took till the ancient Greeks and Euclid's Elements for us to show that there are in fact only 5 Platonic solids, and you can't make a 6th by these symmetrical shapes on the side. So there the artists, these Neolithic stones, were kind of understanding this way before the scientists. At the same time as the ancient Greeks, of course, we started to experiment with, well, what if the faces of these shapes are allowed to be different? If you think about a classic football, it's made out of pentagons and hexagons. So these are the Archimedean solids, and they were classified, I'm trying to remember, are there 14 or 13 of them? Let's say there are 14 of them. I can't remember how many there are. Does anyone remember how many Archimedean solids there are? Okay, good. There are 14 of them. And Archimedes identified 14 of these, but actually what they were turned out to take a long time. We know Archimedes has said, I found all of these things, but then it was kind of lost what they were. And it took until the Renaissance for us to rediscover what those shapes were that Archimedes had discovered, because it took the painters who could actually paint these things, and it became a kind of obsession of Renaissance artists to include symmetrical shapes in their paintings, for us to rediscover these Archimedean shapes. So again, here we see a nice partnership between the mathematicians and the artists. We needed the artists to actually help us to see these shapes that had been discovered before but have been kind of lost since antiquity. And of course, these shapes are very useful if you want to prove how good you are at perspective, because they're very unforgiving. If you've got a tree, it doesn't matter if you get its slightly proportions wrong. It will somehow still look quite tree-like. But a symmetrical shape, if you don't get it right, it looks very obvious. So here's a beautiful example of the portrait of the mathematician Luca Pacioli. And I mean, you already see the dodecahedron, the 12-faced pentagonal shape on the table there, but it's this very curious shape floating in the top left-hand corner, which is made up of triangles and squares. This is one of the Archimedean solids. It's called a rhombicubo-octahedron, and it took to the Renaissance for these shapes to kind of reappear, because these artists could actually paint them. Luca Pacioli actually he wrote a book about these Platonic solids and Archimedean solids, and he employed probably the best illustrator you could have, which is Leonardo da Vinci. So Leonardo, of course, if you're going to choose one person who perfectly encapsulated the science and the arts in one person, it would be Leonardo. And he was the illustrator for many of the shapes that appear in Pacioli's book. Now, there's also interesting uses of these shapes we've seen two physical, the choreography, and also physically on a painting. But there's a very interesting example of some of these Platonic solids being used as a structure for composing music. And one in particular, which I've become totally obsessed with, is a cello piece by the Greek composer Yannis Xenakis. This piece is called Nomos Alpha. Yannis Xenakis is an interesting guy. He was a Greek composer of the 20th century. He was also an architect. He worked with Le Corbusier. Le Corbusier is one of the big characters in the book because he used a lot of ideas of Fibonacci numbers and golden ratio. But he was also, Yannis Xenakis was a composer. And he wrote this amazing piece for solo cello, which uses the symmetries of a cube to structure the piece. So it's a piece basically, it's got 24 variations. It's kind of a pretty crazy piece. And I've started learning the cello just recently, so there's no way I can play this piece, but I got interested in it just as a kind of how was Xenakis using the symmetries of a cube. So the way he does uses the symmetries of the cube in this piece is that he takes a cube and then on the corners of the cube he puts different kind of musical ideas that the cello can play. So a cello can do pizzicato, it can do glissandi, there's an effect where you turn the bow upside down and hit the strings with the wooden part of the bow. And so he puts all of these 8 different ideas the cello can play on the corners of the cube. And then there's another cube which is controlling dynamics. So there will be different dynamics, very quiet, very loud. There's another cube keeping track of how long you spend on each of these things. And then on the first variation, he plays the corners in a particular order. So I'll play you the first variation, and then I'll show you how he moves on to the next variation. So the first corner is like very pizzicato, quite long spent on that one, quite loud, and then it moves across. Actually makes little tetrahedrons. There are 2 tetrahedrons you can put inside a cube. Not long spent on that corner. That's the glissando. And then at the end of the variation, the cube is moved with one of its symmetries. And then it starts off on the next journey. But it plays the corners now in a different order. So the symmetry has moved the points around and it will then just trace out the same trajectory, but now it's doing things in a very different order. So this, as the piece goes on, you're starting to hear with this kind of restriction of the symmetries of the cube, something about the cube as you listen to the piece. Now, there are 24 symmetries, rotations that I can do of a cube. There are 24 variations in this piece. So my immediate assumption was he had a symmetry for each of the variations. But as I began to examine this piece a bit more, it turned out that wasn't the case. And actually, Xenakis was doing something rather special and new, something I've never seen before. What he did was, so you probably know about the Fibonacci numbers. They go 1, 1, 2, 3, 5, 8, 13. You get the next one by adding the 2 previous numbers together. So 8 plus 13 is 21. And so they gradually grow from the previous numbers. What Xenakis did, he said, okay, I'm going to start with 2 symmetries. Then the third variation is going to be what happens if you do these 2 symmetries together. You'll get a third symmetry that the cube will be set in. And then the next symmetry will be the 2 previous symmetries put together, and you'll get a new symmetry. Now, if you keep on doing this, because the symmetries of the numbers are infinite, but the symmetries of the cube are finite. So after a certain while, actually you repeat back to what you started at the beginning. But if you choose different symmetries of the cube, you can repeat quite quickly, just in 6 moves. But what Xenakis found is that if he chose his symmetries carefully enough, and he did this kind of Fibonacci, making the next symmetry of the 2 previous 2, the longest chain of symmetries that he could get is 18. And so there are 18 variations corresponding to each of these Fibonacci symmetries. And then every fourth symmetry, every fourth variation is actually a kind of free-form piece. So in between of those, so you get 6 kind of free-form movements, and then these 18 symmetries which are made out of these kind of Fibonacci symmetries. Now, I have never seen this. I'm a group theorist studying symmetry, one of the things I do. I have never seen anybody exploring this structure in my subject. So, often I get asked, okay, clearly mathematicians, artists, enjoy plundering the mathematicians' cabinet of wonders. But is there any time the artist actually tells the mathematicians something new? And this has actually started a new piece of research for me where I've been trying to explore, well, what about other symmetrical shapes? What is the kind of maximal length of these Fibonacci things? And it seems to be very, very wild. It seems to be very hard to pin down. So by studying this particular piece, it set my own research in symmetry off in a completely new direction, which is kind of fun. Now, these shapes don't have to just live in 3 dimensions. You can start to make Platonic solids in dimensions beyond our physical universe. And somebody who enjoyed doing that was Salvador Dali. He got obsessed with mathematicians talking about the 4th dimension, 5th dimension, shapes in higher dimensional space. And he has this wonderful piece, The Crucifixion, where this is an unwrapped cube, 4-dimensional cube unwrapped into 3 dimensions. If you think about how you make a cube in 3 dimensions out of a piece of paper, you make a net which is made out of 6 squares, so 4 down the center and 2 on the side, and then you wrap those 2 up in the 4 rounds and you make a cube. A 4-dimensional cube is made out of a 3-dimensional net made up of four cubes stacked on top of each other and 4 cubes around the outside. And if you had 4-dimensional space, you would join up the top and bottom cube, the 2 on the side, and then we've run out of space. But at 4 dimensions, you'd be able to join it up to make a cube in 4 dimensions. So I think Salvador Dali, he was a very spiritual man as well as being interested in mathematics. And for him, this idea of the 4th dimension was like a spiritual dimension that we couldn't see, which is why it inspired him, I think, to do the crucifixion of Christ on an unwrapped, something from 4 dimensions projected down, unwrapped into 3 dimensions. There's an interesting novel which uses the same idea, actually. This is called a tesseract very often, this unwrapped 4-dimensional cube. And Alex Garland, who became very famous for writing the book The Beach, made into a movie. His second novel, he got very obsessed with this shape of the tesseract, and he tried to write a narrative which had kind of like 4 independent narrative directions, which somehow you were looking at this shape as you read the novel from different perspectives. These narratives didn't quite interweave until you'd finished the whole book. It was a tour de force of kind of structural writing to be able to keep these narratives together. But he described how when he delivered it to his editor's kind of face went white at the idea of this mathematical structure but underpinning this thing. So I think this book is out of print now because it didn't, you still get The Beach, I think. But, great. How are we doing for time? Oh, I think we should probably, there are many more shapes I could take you on, but we're reaching time where I want to get you to ask some questions. But perhaps I should just end that, I've talked about this connection between the arts and the sciences and shown you a lot of examples of artists inspired by mathematical structures. But I think the converse is also true, that a mathematician also needs to have a bit of the artist about them to be able to create really exciting mathematics. Mathematics isn't just about proving all the true theorems about numbers and geometry. We make a lot of choices, and those choices are very dependent on a kind of aesthetic and a sense of storytelling about our objects. I think a mathematician at its heart is a storyteller. And so we need a bit of the creative imagination, the idea of an emotional response to our mathematics is incredibly important, which is why I think the time I've spent alongside artists, musicians, writers has informed very much the creativity that has led to the mathematics that I've discovered whilst being a professor here. So thank you very much.